Yeah, I think so. Let's go.
Let's go.
Yeah, let's go.
Okay, guys, come on. Is everybody in? Is the people outside? No? Okay, so we're starting our last evening talk. It's a pleasure to have Sara here. Sara is VP of Research at Coir, and she basically kickstarted this Coir for AI initiative that also has like this wide-ranging effect. And we're very pleased to have her again. I'm very much looking forward to her talk. Thank you very much.
Amazing. Thank you. Yeah. So it is wonderful to be here. I know this is the last session of the summer school, so can everyone please stand up? Yes. So what I want to do is everyone stretch up to the side, to the other side, and then high five your neighbor. And now you can sit down. Nice. This is a good way for us to all wake up a bit. So I lead Cohere Labs. I'll share a little bit. This is not what this talk is about, but in case people are curious, we do a lot of work cross-institutionally. We, over the last 3 years, one of our efforts has been to be a frontier lab and to keep publishing. So we've published many techniques about how to build technology at the edge, large-scale systems. We also collaborate a lot, and most of our papers actually are cross-institutional. So if there's topics that are interesting, feel free to reach out. We've released a lot of data sets, so including Aya, which is a family of multilingual models and one of our core focuses. And here's some of the work that we've shared. And here are some of the models that we've released as open weights. I'll just share here one of our core threads, and I'm sharing this because the talk I'll give today doesn't focus on our multilingual work, but if it's interesting, I'm happy to talk about it afterwards. We do a lot of work on how do you expand the languages that models see. So I expanded the languages covered to 101, and we did a lot of this as part of an open science initiative that involved over, I think it's 117 countries. Okay, it is. I always feel like I have to remember. And it involved just thousands of researchers around the world. Also, I'll just share this briefly because it might be interesting. We do offer a lot of research grants, so feel free to apply. You should find it on the website. We try and bridge compute gaps. And so if you want to use one of the models for some of your research, feel free to just email, or there's an application form on the website. And then the final note I'll say before I do the talk is we're about to open our Scholars Application Program. This is a fully paid industry position for a year where you also get access to a huge amount of compute. And we specifically crafted it, so it's for early stage and rising stars who are engineers or researchers, and it's a year-long position. So that's about to open up. So please, yeah, if any of the topics interest you, feel free to reach out. So I work on a few topics. I really enjoy working on efficiency, on multilingual, on reliability, robustness. I'm not going to talk about any of those today. I will be talking slightly about efficiency, but I share this because I'm happy to chat, or feel free to follow up. But what will I talk about today? So I want to talk about two key questions. So it's fun. I tend to use this week actually to think, because normally I now have a very large team and I don't get much time. And so actually I try and update my slides and think, well, what matters to me right now? The first thing I'll talk about is actually something I've been grumpy about for a while. And it's the idea that, we've really relied on these very simple formulas like scaling. But the second thing is something I've recently been thinking about a lot, which is how is our field fundamentally changing, and how are the spaces we optimize in changing? And I think this is actually going to fundamentally change the nature of how we teach computer science and what you learn as you go through your pursuit into AI research. And so I think it's actually very profound, and it's fundamentally reworking our ecosystem. And so hopefully this is a fun way to end the week, because it's asking, what does that mean for us? But first, why does it matter to question why bigger is better? Why ask that question? Well, because it has impacted our ecosystem for the last 2 decades. So we have really leaned into this belief that more compute, bigger models, more data is the formula for success. This has impacted our swag. We now have swag saying GPU poor and rich. It's impacted how companies talk about responsibility. The implication of this scaling policy is that it is inevitably going to happen. So the only question is, can we do it responsibly? Not whether or not we will need to scale. It's also impacted geopolitics. So we now have GPU export controls because the belief is that GPUs are the biggest accelerant of science. Is that true? It has resulted in a shift of contributions from academic to industry research. If you look at this, and this is from the Stanford report, it shows who contributes to top tier research. And you see this concentration of industry in 2022 versus before is primarily concentrated in academia. And increasingly, researchers in industry don't publish, or it's fundamentally controlled the flow of information. It is determined who gets to participate and who doesn't. So this is another chart from the Stanford report, and you can see entire continents are shown to have not contributed to significant machine learning systems between 2002 and 2022, so 2 whole decades. And that's crazy because it's a question of access, but it's also who gets to shape breakthroughs. It has also led to changes in policy. So the EU AI Act had a specific rule about the number of flops for a system to be noteworthy. The implicit assumption is that there is a tipping point, an inflection point for risk, and that is associated with size and amount of compute. And so it is very meaningful to ask, is that a reasonable hypothesis? And what do we know about that relationship? So today I'll start by asking, is bigger always better? And then I'll talk a little bit about what comes next. But to get there, we have to think about, well, what is the role of model size and data in recent breakthroughs? So arguably, it's a bigger is better race. This plot will be familiar because it has been reincarnated in so many forms over the last few years. But it's the idea that we've really just followed a simple formula and that our most top tier systems tend to be really big. This characterizes both tasks, it characterizes multimodal, it involves large increases in both data set and in model sizes. This is captured by Rich Sutton as the bitter lesson. So Rich says the only thing that matters in the long run is compute. It's kind of an ego blow because what it's saying is that we're not, all our fancy hypotheses and theories and fancy algorithms don't matter as much as having something generalizable as a representation. So, that's able to leverage compute and scaling it. So is Sutton right? What do we think? Shout it out. Okay, nod, bravo, excellent. Why is Sutton right? Yes, excellent. Okay, good. So I think what you're saying is evidence supports Sutton. You're right. Okay, but does that make him right? What do we think? Very opening. Yes, go ahead. What do we think? So why is he not right?
So when you have a hammer, everything looks like a nail.
Oh,
Definitely
excellent
yeah.
quote. Okay, so we have what's being said is when you have a hammer, everything looks like a nail. So when we know compute works, we just keep on pounding it. And it might not work quite as well in the future as in the past. I think that's what you're saying. Nice. What else? Why do we think it won't work? Yeah, go ahead. Who's gonna put that? I think do I see a tentative hand? Courage. Okay, excellent. Go ahead. Yep, over there. Mario, you're too good at this. Yes, bravo, excellent. So what's being said here is the architecture matters. Why? Because that's one of the strongest building blocks that you have as terms of a prior. It determines to a large extent your search space, and so we'll talk about that. So really excellent point. Okay, what else? Bravo, yeah, we have one over here.
Better algorithms.
Better algorithms, yes. So what compute might not take into account is that algorithms have different compute costs and some might not require scaling, right? So that's really fun. We'll talk a little bit about that. What else? Up there at the back, yes, shout it out. Data, bravo. Yeah, this is on the bingo card. Yeah, data is really good. What about data? Oh, interesting take. That's not where I thought you would go. Okay, what do you mean? So what does that, so I guess, is that the implicit thing that that chart about the data scaling, there's a limit to that? Yeah. Yeah, so this reminds me of Cho's lecture with the scaling laws. What will happen to the scaling laws if we run out of data? Okay, so who believes that? Who believes we're running out of data? I'm just curious. Put up your hands. It's not a trick question. I'm just really, they could be. Okay, nice. Good distribution. Who believes we're not running out of data? Okay, for those who said not, we're not running. So why are we not running out of data? Go ahead. On the spot. And you even get a microphone. This is too much pressure. Yeah.
Perhaps we're going to be including like context of where things are being created and but
Yeah,
and
you're right.
where so now we
Yeah.
have a text that tomorrow might have like additional dimensions to that piece of text.
Yeah, in some ways, some of the most profound shifts we've had, right, have been about using real world data. And real world data is not static, it evolves. So I think what you're getting at is that the body of available data, it's not a snapshot in time. There is additional data that evolves. Okay, why? I guess the counterpoint to that from someone who believes data is ending is that the rate of expansion, I guess you could, I don't, people would argue it's not quite the same as the rate of consumption of our scaling laws. But I'm curious, what's another counter argument that data is not ending? So the gentleman over there, yeah. Yeah, synthetic data. Yes. I think this is a very important point that's often missed in the discussions about data's set ending. Synthetic data, especially if you have a diverse distribution, you can avoid modal collapse and you can have very rich sources of data and, in fact, coverage. The balance is how do you anchor it to real distribution? So I think that's kind of interesting. But I do agree data is going to be a big component of that. Maybe of this. Maybe there's an argument why I think yours is an argument maybe why there might be a hard constraint, but there's also an argument that investing in data curbs our capacity needs. So we'll talk a little bit about that. What else? Maybe one more and then we'll keep going. Yes. Yes, bravo. Okay, nice. So that's another component to this. So very good. Okay, so there is an argument in favor of Sutton, and I think it was said very well early on. I think who was the first person who spoke? I think it was somebody. Ah, excellent. Yes, yeah, and you're like the evidence supports Sutton, and indeed he did just win a Turing. So empirically, he's been proven out well. Different regimes of capacity appear to allow for different generalization properties, and it's also very simple. For example, we know that different levels of scale impart different properties. Like so something like few shot or zero shot tends to work better at certain scales. And it requires larger and larger models to take advantage of instruction fine-tuning. We see the same with reasoning now. So it's very hard to get reasoning to work well at a 3 billion capacity model. Typically, you see a lot of repetition. So you need certain, in many ways, optimization landscapes to be able to impart some of these more difficult properties, it appears. And also, certainly, if you look at the chatbot arena lately, scale does indeed matter. So proprietary models don't often reveal their parameter counts, but you can even see from the open weights models that have been released, the best performing one, I think, at least at the time I put together the slide, was DeepSeek R1. So that has 685 billion parameters. So these are not light models. And even since, we've seen larger open weights models being added. So scaling is very favored. And I would also argue it's because a lot of this happens in industry. And it's very easy to argue for scaling in industry because you typically have a quarter and you can either argue for a more kind of long-term approach, exploring new optimization, or it's just very easy to argue for, well, it worked in the past, let's try adding a bit more compute. However, I think it's limited because this relationship is not well understood. So models at the same capacity have been getting better over time. So this is a plot of really the best performing model on the LLM open leaderboard that's under 13 billion parameters. So, and you can see this arc upwards. And also smaller models frequently outperform larger models. So in this plot, what you're seeing is the best daily small model under 13 billion versus any model that performs worse over 13 billion. And you can see over time, we have far more bad large models that outperformed by small models. We also see this frequently in our own work. So when we did iExpanse 32B, the scale did private testing. So this is where you can't see the test sets. There's no contamination. So it's the type of test set that I actually really believe in, because I think we frequently release evaluation sets and we frequently observe contamination. And what we see is that it can outperform much larger models, including Claude, Mistral Large, and then Llama 405B parameters. But also, we see it in vision. So we just released IOVision, and we saw that it outperformed often models 11 times its size. So this is against Llama and 90B, and so we see that it both preserves your text performance as well as the vision performance. So in fact, we observe a highly uncertain relationship between compute and performance. And I'm going to lead you through why, and then I think that it's worthwhile thinking through, what do we understand because of that tension? So one that was mentioned, which was excellent, which is data delivers a lot of the need for compute. So we've done a lot of work on what's the relationship between data quality and the amount of compute needed. There's also a fantastic body of work on just the impact of deduplication, filtering, even the conditions in which you scrape. We worked on what is effective data pruning for pre-training at scale. And we found that you can improve over your original corpus with as little as 30%. And so this is at pre-training scale, so it's a massive amount of data. We also show that it's valuable for selecting what humans have to annotate. But the other thing is that this relationship between weights and performance is not well understood. So we see diminishing returns when we add more parameters. This is an example which is old school. It's inception v3 versus v4. And there you see, this is showing that when you double the weights from 21 million to 41 million, you only increase the percentage of performance by 2%. So this seems quite now, like millions of parameters. But with convolutional neural networks, this was the beginning signs of the saturation of this architecture. And what's interesting is that in many ways, it was showing that we now have to add an excessive number of parameters to squeak out new performance. But it's similar again, right? We now see an increased uncertainty from labs in investing in ever larger models, mainly because we're starting to see the decreasing returns from doubling size each time. And this is interesting because it speaks to a fundamental limitation. I think it was a fantastic comment from someone over there about the architecture. Often the architecture is the ceiling of our search space. So when you unlock a new architecture, you unlock a completely different dynamic in where you can search and how conducive your search space is. But over time, if you saturate that search space, you naturally plateau in performance. We also see massive redundancies between weights. So we can predict most of the weights using a small holdout, and we can remove most weights after training. So what this tells us is that the weights, and this is work that we did on sparsity, and we compare many popular methods, and we show that even if you randomly move the weights, so you're just guessing what weights are important, you can preserve a lot of performance. So the random here is that yellow, and up until 90%, it's still pretty robust. And what's interesting about this is that what this is saying is that while weights are critical for getting to a good optimization landscape, once you've achieved that, you can remove many of them. I would say, arguably, so much of this and the relationship that we have with compute diminishing over time is because we pay a lot to learn all of the distribution we care about. So most of our stable optimization techniques revolve around some type of empirical risk minimization centered on the average performance. This means it takes much more capacity to learn rare artifacts. So that's both indexed in the amount of time it takes or the size of the model. Because remember, most of the time early on in training, we're basically indexing for the most coherent gradients, which is typically the most frequent examples in a batch. And the majority of features are learned in this early period. I would also say, and we show a lot of work on this that I'll show, is that we looked at what's lost and gained with model size. And what we show is that removing the weights, when you remove 90% of the weights, what you do lose performance on is just a tiny sliver of the distribution. So most of the distribution is preserved, meaning you actually learn most of your data distribution with a very small model. The expansion of the model is for that massive long tail of artifacts. I think this realization is worth understanding, because what this is really saying is that when you scale a model, what you are really doing is you're paying a lot to learn rare artifacts in the real world. And it's fundamentally different from how we navigate the real world or the robustness with which we do it. We're paying an enormous cost to learn a small amount of samples. And this is work that we did, which was really interesting. It shows just that learning trajectory, and it shows that those rare examples are learned so much further. You can actually use this to decouple between noisy examples and rare examples, because noisy examples, so totally stochastic examples that have very little value for learning, are learned the last. And so it's really interesting. We often talk about sources of uncertainty. In machine learning, we typically don't distinguish sources of uncertainty. We only assign probabilities, which often intermingle the two. But I think treating this as understanding the sources and using markers for what the provenance of noise is, so whether it's reducible or irreducible, irreducible noise is learned the last, because it frequently has to be memorized. It can't be learned from coherent patterns. So I think that's really interesting in terms of thinking about how we treat these different groups. So where do we end up? So I think this gets to really the new things I've been thinking about this week. I may have convinced you that we're now in a period of decreasing returns to compute. But I don't think that matters, because I don't think I have to convince you of that. I don't have to convince you that sudden is wrong going forward. I just have to really convince you that it's very expensive to continue to take the path, and that in many ways we pay a lot to continue this formula of scaling the weights. And as a point of comparison, our brain is incredibly efficient. So we have 85 billion neurons, but we run on the energy equivalent of an electric shaver. And we have key choices used to embed this intelligence to make it much more efficient. For example, our pathways are optimized. If you walk and talk, it's much easier than if you walk and read. The same way that if you spot something notable, you're going to register it, but largely you simulate what you see. So if there's nothing that changes in your environment, you are literally not doing a full backward forward pass. You're simulating. That saves us a ton of time. It also means that we have incredible saliency. We drop most information, which makes it much more efficient. In contrast, our networks are really painful. We still train in this really belabored pre-training fashion. We don't apply adaptive compute meaningfully at scale. Typically, at a foundation model company, you still produce the general model, and then you give it to someone else to host it, which is not really the way that eventually we want to learn, which is we want to adapt and respond to immediate context. And our global updates mean that it's very hard to add new data to models. Typically, when we do things like fine tuning, it's a really delicate balance. We have to do things like LoRa and differentiated learning rates and be careful about how much data we add. And all this means that we pay a lot to learn. So I think that is what gets us to the next question. What happens next? This is the fun part. So I like this quote. What we have before us is some breathtaking opportunities disguised as insoluble problems. So modern computer science is very young. It's only been around really since the late 1950s. So the Dartmouth conference was in 1957. What that means is, if you think about it, the rapid change in both our tools and the pace is pretty absurd, but it also means it's still wide open. So all of you are in this field and pursuing research. The very nature of research has radically changed over the last 2 decades. But throughout this, and throughout these 75 years, it's mainly been centered around the model. So the early perceptron or the early symbolic algorithms, which typically were very much the pursuit of something that's modular. Even the way that we think about our own intelligence and how early AI researchers talked about it was like imitating a single person. Although I think it's a valid question about whether our intelligence is truly individual or much more collective. Because I think in many ways, if you just tried to imitate like a single human, you'd end up with not a great system. I think a lot of how we create really, truly interesting patterns of collaboration is that we have this need to gain the respect of others. It influences a lot how we do very cheap global updates. But this obsession with just a single model and creating this has been at the center of our field. I would argue that we're now at an interesting time where our tools for optimization differ. One is that our data space has become malleable and open for optimization. And the other is what I would call gradient-free performance updates, which I think are pretty profound. But let's talk first about optimization in the data space. And I'll talk about two directions we spend a lot of time on as a lab. Data pruning, I actually won't speak about as much. I think I've shared some examples previously. We do a lot of work on it. The idea here is that you isolate for rare examples and you remove redundant examples. Okay, that's not mine. Good. Someone else is in trouble. Good. Nice. um, but I think this is important because it means we spend more capacity on certain examples. It's kind of a hack. We're saying, oh, because we do empirical risk minimization, our objective, let's just make sure what we average over is the examples we care about. But it's an effective hack, and it is in the data space. But this is the one that I really want to talk about because I think this is really interesting. We are increasingly moving away from static data sets. And this is important because ML researchers have traditionally treated data sets as fixed. They're expensive to collect. So Desmond gave a whole presentation earlier today about how difficult it is to collect data sets and evaluation sets across languages and domains. And so once they're done, once we have that, we treat them as fixed. We don't update them normally. We're like, great, we finally secured the data. What can we do around it? However, this is now changing because the implication of that was that we were stuck with the quality that we collected. And the other implication of that was that even if the problem evolved, we couldn't update to fit the problem. So the taxonomy that we chose at the time, we were just kind of stuck with it. It meant that it mattered a lot. What was the quality of the instructions and the taxonomy? And most of machine learning has been built around this principle that we have some sample, a random sample, an IID sample from an underlying distribution that we want to model. But that is changing because in many ways, that's the source of the inefficiency, right? Because if it's IID and we can't really control like the composition, we end up doing all these acrobatics around it to try and get stratification, to try and get balancing. I think this is what makes this shift so profound because it allows us to direct and make the space much more malleable. And this is largely possible because of advances in synthetic data that allow us to imagine as such. So, even the idea of taxonomy, so you can have real underlying data, but you can create innovative taxonomies or metadata. That's all been unlocked by having fairly cheap ways to retag and reposition your data. Of course, it all rests on the quality of your teacher, but I think this is important because it allows us to oversample from some parts of the distribution that we consider more important. And then this fundamentally changes how we treat that stratification problem. We did really nice work around this that I want to point out, which is that once you know that, you can also explicitly steer the data creation space. So this was work led by Louisa, but it also means, if you follow this to the conclusion, that you can steer it towards non-differentiable objectives. So we've been stuck in this differentiable optimization setting for a long time. We use gradients. Everything has to be really behave nicely and give us stable gradient flow. This is actually really interesting because it means we can optimize for non-differentiable objectives as a way to steer the data creation process. And it means that over time, we can explicitly control the attributes of our data set. We also show that you can drastically avoid this mode collapse. So a lot of the counterexamples for why you can't use synthetic data as a complement for data running out is that, oh no, it's mode collapse and it results in gibberish. But actually, I think you can avoid that by adding diversity of your teachers. So the main example of mode collapse happens when you repeatedly train on the outputs from a single teacher. And what we show is that if you strategically sample based on who's the best teacher, so similar to how when you learn a music lesson, you go to a music teacher, you go to French, you go to a French teacher, you don't use the same teacher for all those things. If you arbitrage in that way, you can have powerful benefits from the diversity of data you're able to create. But here's the fun part, and I think this is actually what's fundamentally also going to test the discipline and how we structure teaching. What can we do when we don't allow for any gradient updates? So what are some optimization approaches that don't require any gradient updates? And let me see time. Oh, nice. Okay, great. I always like to leave a lot of time for questions, so we're on track. Nice. Okay, what do we do when we don't allow any? Yes, go ahead. Yes, bravo. What do you mean by what's an example then? Yes, 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 yes. So what was said was RAG and inference time injection. That's one example. So RAG, yes, it often requires very little parameters to add a database. Yep. Okay, go ahead. Who else? Yep, go ahead. Ooh, what do you mean by model steering? Yeah, yeah, that's interesting. So you can do that with no, typically, I think people typically use small types of data to steer it to understand the sensitivity, but you're right, you don't actually update the gradients using, sometimes it doesn't use an objective. Sometimes you can just jitter it. So maybe, yeah, in some circumstances, yes, but nice. Okay, I like that. Okay, go ahead. Yes, bravo. Decoding, yep. So decoding, like what? Go ahead. Yeah, so I think what's being said, nice. I think what's being said is that like how, maybe for certain types of problems where it's factual, you might use something like you might have multiple samples and measure something like consistency. Beam search was also mentioned. So there's both like how you sample, the number of samples that you have, and how you aggregate that information. Those are all things that you can use. And I think what you're getting at is very nice, which is that we should be changing that by problem. And there's some work around this, but I actually think a lot of it is still very ad hoc. And I think it's quite fun to think about what that would look like as a more nimble optimization problem. So that's very fun. Yeah, what else? What else? Okay, excellent. Yeah.
The lowest hanging fruit, prompting and the zero.
Yes, I like this. Yes, absolutely. Prompt engineering, right? So that was the first way people tried to have controllability over this space. What else? Okay, three. Yeah, I'll take one, two, and then three. Yep. You can go first. Yeah, gentleman in the white t-shirt. Oh, fun. So when you sample something, so you have a prompt, you get a generation, and you're estimating the quality of that generation using another model? Okay, nice, nice. So this is another version of like the multi-generation setting. So maybe you'll, instead of prompting once and gain generation, you might get three, and then you score it using another model, and then you return the best one. So this typically provides pretty pronounced gains. You can think of the multilingual arbitrage paper I showed. You can think of doing this, but just not under a serving condition because you're creating data sets then you train on. But you can also, it's frequently used in an inference condition. Typically, the fun part there and what people have to balance is what's your latency? Like, how many generations are you going to give yourself before it's intolerable? Yeah, and I see you're nodding because we have someone from Google who's serving models, so I think that's top of mind, right? Yeah, I think for typically if you're serving a model and you're productionizing it, you're always thinking about how am I firstly, how many replicas, instances of the models do I have? And then what's my serving budget? Like, how am I allocating it? So it's really important. Nice. What else? Who's up there? Excellent. Nice. I was about to. Pardon? Go ahead. Say it again. Matrix factorizations. Ah, go on. What do you mean by that? Yeah, so typically the tricky thing is you need some recalibration. So it tends to be quite sensitive if you don't recalibrate the weights. It's got similar problems to sparsity. So you could get away with one-shot sparsity, and there's a lot of work on doing it. So yes, I think there's some fun work that technically does one-shot, but most need some type of fine tuning stage to make it as performance, to not degrade. But I like the direction. In general, architecture changes are quite interesting to do, um, to think about because you could gain a lot in terms of acceleration. Yeah. And we do some. What's one example of an architecture change that often is one shot that we don't have to recalibrate as much? Yes, nice. Great. Yeah, exactly. We often do quantization as one shot. Here's the tricky thing is the larger the model, the harder it is to do as one shot. It tends to be all the at the extreme, the smaller the model. So like a 3B model is extremely sensitive to quantization. And that's why you see these like weird artifacts like bad reasoning, but extremely large models are also weirdly sensitive to calibration. And so it's really interesting. It changes the type of quantization methods you're able to use. And so actually we do a lot of work on that too. We show that there's some sensitivity that emerges after 8B due to essentially because the networks get so deep, the activation spread becomes more extreme, and it means that your quantization values become more skewed. So you just have to be careful of that, and you have to treat it when you quantize. So that's quite fun. Okay, what else? One more here. What do we think? Pardon? Paralyzation. Interesting. Go on. So how would that, okay, so what would that give us, paralyzation? Yeah, that's true. I guess we've inadvertently turned into efficiency. Yeah, okay, cool. Yeah, I think that would give you, it wouldn't necessarily give you, it would actually preserve performance, but it would give you a lot more ability. And actually, that frequently is a strategy when you're serving, is to try and parallelize requests. And probably a more interesting strategy that's not often talked about is routing requests. That's also quite fun, right? Because we often think of these models as monoliths, like you have a single model, that's the model that's talked about in the paper. What's more fun to think about is typically when you're serving, you maybe have multiple replicas of a same model or different versions at different sizes. And there's fun stuff you can do there if you think about adaptive compute. Okay, so we are in an era where I would argue we can start to learn on the fly. And why is that? Because we don't need gradient updates. And I'm going to talk about three things. So one is changes to the model itself. I think RAG was mentioned. I'm going to talk about merging because I was saying this during the coffee break, but actually in our lab, we focused a lot on merging, mainly because we made a bet on dense models. We release as open weights a lot of our models, and mixture of experts are really painful for developers to self-host. So actually we focused on really big dense models. Merging tends to work extremely well for dense models. And that's partly, it's very interesting. It's interesting how choices about some aspects of where you're going to place bets have these implications on what research tracks you really push on. And for example, for us as a frontier lab, I think there's probably only one other frontier lab that kept dense. That was Llama for a while. And then they ventured with Llama 4, arguably not so well into mixture of experts. But I think because of that, we've really done a really nice work on merging and the benefits it can bring. Whereas if you are a lab focusing on mixture of experts, so OpenAI is a mixture of experts, that's much harder to do. So merging doesn't provide as much benefits there. So it's kind of interesting. It impacts like what questions you work on as well. And then I'm going to talk about, inference scaling, and then I'm going to talk about conditional responses, which is kind of fun. Okay, so I would argue we've moved this way in this chart. So compute heavy would be how we started. Things like extensive pre-training, you need considerable data. It's all those earlier charts which showed upwards, bigger is better. I think now we have so many compute light methods that really dramatically change performance. This includes synthetic data, fine tuning, and includes a lot of structuring of data. Like people think of reasoning as like an optimization problem, but arguably I would think of it as another multitask IFT breakthrough. It's more about this, at least in its current form, it's more about the structure of data that has been helpful than it is about any profound like jump forward in the actual optimization, which is kind of interesting. And I actually think that structure of reasoning as a grumpy aside is probably likely to change because I don't think, right now we get these massive reasoning traces. There's not much reason for that to actually be in that form or to be in the output space if you think about it, because really it's just inducing the model to spend more time processing and thinking through that sequence. Increasing context length, but then we have these gradient free methods, right? Which is like the best of n sampling that was mentioned with the reward model. We have tool use, which no one mentioned, but is actually pretty profound, right? It often requires some fine tuning, but often it can be zero shot tool use. So that can really amplify your area and your purview of use. RAG was mentioned. agents wasn't mentioned, but it's very much part of this, right? So when you have multiple models working together, how does that amplify? I'll speak about merging first, and I'm going to speak about these three buckets. So you can think of merging as like bonsai grafting. I don't know who's worked with plants. My husband is obsessed with bonsai, so this metaphor is very clear for me, but I don't know if other people share this obsession. It's kind of weird. But in bonsai, typically you graft from the plants that you think have desirable properties onto your plants. And I think this is a fundamental change in the paradigm because typically we've thought about the whole model process as draining a lot of training and data and compute to produce a single model. And once it's done, it's kind of static. But now with merging, we can almost add new capabilities very quickly and often in a one-shot way. Model merging combines two or more models, and often it does it in a very simple way. I was talking to the gentleman, I think, who may be sleeping. Oh, that's a bit awkward for him. But he's doing a fantastic research on merging in the vision space. And I think this is a very nice example. You can do very simple interpolations. So you can average the different models. And merging often requires no additional training, and it often preserves performance when introducing new capabilities. I want to emphasize this because this is important, because we did this work on safety. This is led by Akansha. It's very good, but this one is actually really interesting. So when we extended AYA to multimodality, we would see massive text degradation. And in fact, all these models, which are fine-tuned, so essentially you add the capability, that you add in the vision capability and you do extended fine-tuning, you see massive degradation. So even with Momo, you would have 44% and you would never regain it. So we can avoid this by merging. So actually when we merged, we were able to not only retain the text performance, but we actually saw improvements. And this is very nice because it's also data, doesn't require data. So if you think about how actual everyday communities use these models, that changes their notion of how they can add in new capabilities. The difficulty is that you need models with the same architecture. And so there has to be an emphasis on, if you're going to do open weights, the most valuable type of open weights is if you can release some of these candidate models that could be good merge candidates. And we've done a lot of this. So we've used this across our work. Inference time techniques, we mentioned this. So I think of this as the following, is that, you know, in the old paradigm, we spent all this effort building a single type of tree. And now all of inference type paradigms, all the descriptions that you heard there is really about how to choose a fruit. It's like obsessing, like, what fruit do I choose? How many do I select before I choose a one? Or how do I squeeze them together and make the best juice? Like, that is inference time scaling. You're stuck with your tree. So if your tree is bad, you're kind of stuck with it, but you're really taking your time to choose the best fruit. We recently did a paper which appropriately captures this metaphor when life gives you samples. And this is really nice work by Amar, but we do an extensive study of this in the multilingual setting. And what's really nice is it just shows the gains that you can get even for really strong models. What I want to highlight here, so Command A is a super performant model. It's 110 billion parameters. It's a flagship model, and you can still get 10% gains just with 5 samples. So this is really profound and changes the whole calculus. And then I want to end by talking about controllability and also where I see it changing the space of where we do research. So I think that in my mind, this idea of controllability, it's to remove the burden from the end user. So right now with these examples, the lemon tree's there and someone has to go figure out how to pick. Here, I think it's about giving a ladder. Right now, we put a lot of pressure on the end user to figure out how to write the perfect prompt, how to know how to condition the model, how to figure out all this stuff. And actually, I think continuous learning from our perspective as computer scientists, as people who are building algorithms, is to expand that algorithm space to learn how to do this for the user. We treat shipping the model and then we walk away. Paper done, cool. And actually, I think the truth, the holy grail of what we want to do, which is adaptive learning, navigating, interacting with the world, requires us to think about how do you adapt a model using all these gradient-free techniques in place to this response. So one of the papers that we recently released here is we released a paper led by Daniel, who's fantastic, treasure hunt. So we condition the model during training to actually have a very rich taxonomy of different metadata. But then we infer it automatically. The model is taught to infer it based on an incoming prompt. So it means that the rich taxonomy is there to condition the space, but it's out of the user's hands. Like we are automatically learning it. And this leads to really strong gains in performance, but most importantly, the majority of gains are actually in the long tail. So we see 9 percentage points win rates in very rare tasks, and more moderate, like 6% in the more frequent tasks. And this is really giving controllability, but not expecting expertise, and meaning that it's much more about the model itself learning. I also think that this will require co-design of model and interface. Why? Because increasingly, the most intelligent system will be one that interacts and learns and updates in place, which means you need to understand how that interaction occurs and also respond to it. This is up by Luke. So we just released this last week, but it's an attempt for us to really allow people to give more granular feedback. But also then we update in place, right? So I did this about the Lisbon Summer School today. So this is an example. And it said, oh, it's 1 to 2 weeks. So I said, okay, it sounds pretty aggressive the way I wrote it. I said, it is only 1 week. But then the model updated in place and it responded. And this is important because right now, feedback is thankless, right? So you give feedback, it goes into a void. We need much more essentially learning in place and adaptation in place. And I think this is going to change our field because it moves us a bit further away from the idea of a static contribution. And really now it's about how do we build models and optimization approaches that allow for continuous learning, where we can continue to adapt to how the model interacts with its environment. So where does that leave us? So on a big picture level, I think that these gradient level improvements and these gradient free are more like our own intelligence. I think I mentioned that before, but for me, I think that we are very successful as you know, the way that we have achieved as a species, largely because not because we're particularly smart, but because we have strong social bonds to each other, and we are very good at coordinating because of that. Like we're all in this room right now. I think that us using more of these pools of models or gradient-free techniques moves us more in that direction. Undoubtedly, however, our biggest prior on our search space is still the architecture. So I think that came up early in this talk, but it's so true. A lot of what we're doing now is we're creating interplay between models or richer environments. But if we have a change in the fundamental building blocks of the architecture, we're still going to see corresponding much more rapid gains in scalability and performance. But I think that will require maybe a fundamentally different combination, right? With a different combination of hardware, software, and algorithm. I think that's what makes this discipline so fun and in some ways so meaningful to be so early on in modern computer science. And I actually think scale is probably the least interesting problem solution to the problem, because it kind of turns us into hardware architects. Like we're just adding more transistors to the chips. And this is now the much more fun part, where we're able to add additional kind of techniques, but bend the scaling laws so we achieve a lot more with efficiency. I do think that one trade-off of this is I think it will further amplify the divide between academia and industry. If the most intelligent system is about interaction, it matters who controls the environment, and it matters the breadth of that environment. And so I think that's something that we have to think about and intervene aggressively, because it will further also mean that the notion of how you represent your progress is going to become more challenging, right? These type of rich continuous learning interactions are hard to represent on a PDF that's 9 pages. But I think it makes our lives a lot more interesting. And it means that the next 10 years are going to be very fun. And probably what you learn in your introductory machine learning classes is going to fundamentally change yet again. So with that, Thank you. Let's open it up for discussion. Thank you. Excellent. Oh, perfect. Okay, nice.
Thanks for the talk. So I have a question. The previous days, Lucas, I think the guy from Google, he was saying he was kind of advising us all, like, hey, be excited about applications that go beyond chatbots, right?
Yeah.
So I'm curious, like, what are the applications beyond chatbots that maybe you're excited for? And are there any technological or knowledge shortcomings that prevent us from deploying LLMs in these applications?
Oh, did Lucas say what his answer was? That's kind of fun.
Sorry?
Did Lucas reply to this question or did he keep it
No,
top
no.
secret? Okay, nice.
I didn't ask him that question, but
So I think so it's interesting. So one of them I kind of showed this early preview, right? You can have a chatbot, but it's typically treated as a monolithic. I ask, the chatbot responds. But the idea of an interaction which is richer, like direction or adding more granular feedback, and then in place, updating, I think that's much more interesting. Or right now, the notion of agent is represented as a terrible graph diagram. You initialize your agent, send it, and like, that should just be much more visceral. Like you should be able to just take an agent, shove it to the other side of the screen, and it should go do something for you that you've already typed out. So you should be able to indicate a much more primary intuitive ways, like what you want, how you want the complexity to be treated in your task. Because a fundamental theme throughout this is that the solution and the complexity of the solution should differ across the distribution. So, I think you brought it up yourself, this idea that different tasks should demand different sampling techniques. So I think that is probably the interface is a facet of that, right? There should be some way which is intuitive for the interface to indicate the complexity and for you to dial it down if you don't think it's appropriate. I think things like that are fun to start surfacing to people because right now the tools that we surface to people are like temperature, which no one really gets who's outside of a machine learning school, and basically it's just a hacking lever, right? Or people feel the need to write all these prompts. The other thing that I think will happen is that documents will be automatically populated in context, meaning like I think that right now you have to add the relevant documents to a question. But if you've given access to documents, I think it's much more interesting once your prompt is written, it just automatically pulls it. I think stuff like that is really cool. But the other thing, maybe I'll share this. Right now, we show reasoning traces. I think the novelty of that is worn off. So unless reasoning traces become useful to everyday users, I think we just don't want them for very long. But there are ways to make it useful. Like you could imagine even what I showed here, which is this kind of fun, you add a comment, like it's also fun to think of that as a dynamic interplay, right? So that would be interesting. Like if you can perturb parts of the reasoning trace and alter the sequence. I think that's the way we should be thinking about some of these things. But yeah, nice question. What else? Go ahead. Yeah, you feel free to shout out. And then maybe I can take a few more. I think we have maybe 4 minutes. Yeah. Maybe we can do this one while we're waiting for that one.
So thanks so much for your presentation. I really like
Okay, so
your comments. I really like sort of this idea of a gradient-free improvement model future.
yeah.
And it seems like you've tried to bake that into one of your multilingual models from what you said. Like it sort of responds very well to inference time compute.
Yeah.
And so the question is like, can we optimize our models to be primed for inference time compute?
Yes. Yeah. So like
yeah.
yeah, I think we can. I mean, even this was a primate, right? Because we had to condition the model during training to expect this complex taxonomy. But you could imagine other ways of training with the view that you're going to leverage this conditioning. So I think yes.
But are there things that we can do like in the pre-training phase, for example, that explicitly primes, the model to know you're gonna have to be a good in-context learner?
Yeah.
Or yeah.
I
Yeah.
think so. I think there's already work that shows how you treat pre-training dramatically impacts the benefits of alignment. For example, your pre-training is kind of your, so one of the reasons it does that is that a lot of alignment techniques exacerbate kind of probability distribution. But if you already have very skewed probability distribution from pre-training, you end up overfitting a lot more quickly. So if some instances are zero probability already after pre-training, your alignment is just going to further amplify that. You can't correct or introduce new behavior. So there's certainly already things like that where we see that implication, but it sounds like you have something on your mind.
I do have.
Yeah, I know. I
but
can
I'd like-
tell from how you asked the question. Nice. Okay, we'll talk. We'll talk. Nice. And then we missed the lady over there, and then there's one in the back, and then maybe we call it because I know Ramon has to do a very impressive closing ceremony. So yeah. So sorry. I think you had a question, right? Yeah.
Thank you for your presentation. I was wondering about the human in the loop feedback loop you mentioned, and I was thinking these models already contribute to so much misinformation. How can we implement that in a way that's first safe in that sense, and also safe regarding, for example, LLM attacks and stuff like prompt injection and things like that?
We can't. Yeah, I think that it's yeah, I actually think misinformation is one of the biggest risks that we haven't. It's interesting because people talk a lot about misinformation, but I also see it in other use cases like scams, you know, like now with audio and with text and with very realistic emails, just the threshold to misuse is a lot lower. So I think this is one of the most pressing and urgent possible misuses. Our tools are largely limited by the fact that so much of this is a facet of the ecosystem. So the common solution I get to this, and I've brought it up a lot, like this is urgent, and policymakers don't really want to talk about it because their common solution is, well, all the media platforms already have their mitigation techniques for this. However, I think what's underestimated is that the barriers to entry are much cheaper, so you can try more things. So that's where you get this adversarial nature. I think that you know, things like watermarking, which is typically one of the things that is suggested as a solution to this, they raise the barriers to misuse, but they don't eliminate it. And so I think it's really important direction of work to understand combination of defenses because this seems to be the most plausible. It's not treated in academia. Why? Because in academia, we love problems where you can precisely prove. And actually combination defenses are from academic perspective very hacky. You basically combine multiple defenses and you expect you can at least tell one is present. But engineering wise, they're the most effective defense we have. So even with prompt attacks, typically the strategy is not that one detection method will work, it's that you have a combination of detection methods, and often they're cascading. So this is important. It's a very good question. Maybe one last question from the back. Yeah. Okay.
Thank you for the great talk.
Thank you.
I totally agree with you. And at some point, there was a slide about the big picture and human intelligence.
Yeah.
Yeah, when I think about the way we learn things, I mean, sometimes it is like trial and error. The way we human beings act is like to reduce an error and to maximize the revenue. So if you want to, create agents that can act like humans, somehow it is difficult to cancel altogether minimum problems. So somehow you are searching for an algorithms that can find minimum of a function, but without gradient updates. So do you think that the new paradigm we are searching for can somehow search minimum without gradient updates? So that's the question.
Oh, I guess, is that a signal that I'm meant to leave the stage from above? Okay, maybe maybe I'll just say this. I actually think what you're getting at, so forget the minimum depiction of this problem, because that's very difficult, right? To formulate it. You would need an objective that you're confident about for coordination. However, and that could be characterized with, minimization. I do think the first step towards that is just thinking about how to have a more disciplined coordination approach. If you look at most agent setups right now, it's literally like someone went on the whiteboards, like, what can we slap together, put on a blog post, call it a day. But there's not actually a learned behavior and how agents interact. And that's the fun part, right? So I think this is the nice part that you're getting at, which is how do we learn? How does a model learn what agent it should interact with over time? And how does that become something that is learned and not dictated by a logic? Because right now, agent charts are mostly logic charts. You're allowed to do some things, you're not allowed to do others. That's the fun part of the question. So I think you're on the right track. Nice. Okay, I think that's it. And I'm going to pass. Oh, go ahead.
Can I ask you-
Yes, you must.
Triggered by the last one.
You must.
What if you don't have an objective to minimize? You know, there is a lot of interest in open-ended learning where you want to have models that are driven by curiosity and explore.
Yes,
something
yeah.
interesting. Do you have any comments on that? This is more optimization free
Yeah.
as opposed to gradient free.
And by the way, I do think we're back in that regime. So the reason why reinforcement learning worked so well over the last few years is that we had a very well-conditioned search space. Because even though you were trying to predict the next token, and that could be very large, in fact, it's by the time you pre-trained a model, post-trained it, it's very well conditioned. So all the reinforcement learning researchers were like, no, it works. Everything we've been talking about works really well. But now we're moving back into a much more traditional RL environment where the search space is much larger. If you think about agent sequence of actions, like even the one that people love to talk about, like, oh, navigating to go book a table at a restaurant, that's a much more complex step by step, and there's dependencies. And oftentimes it's a bit more sparse, the reward, right? Because maybe you have to navigate to a website. Do you get a reward for that? How do you know that it's the right website to give a reward? So we're back in that era. I think we're not very good. Our models are very brittle in multi-step dependencies. And so how we handle that and how we give a placebo reward is very interesting. It also, you'll see in very radically different approaches. Some are doing browser-based. The other are doing more generalizable, more agnostic. So browser-based even, a lot of the solution to this is by controlling where you can search. And so you control it and then you're over-simulating. So you're just learning dependencies. So in some ways, this is away from RL, and you're dealing with the lack of dense rewards by simulating so many rollouts that you almost create like enough pseudo, supervised examples that you can learn in. This is the least interesting way, right? The most interesting is what you're talking about, which is we move away from our pseudo supervised setting where we've just exhausted the search space by simulating so much, and we have some other type of reward that doesn't have to be the final one, but gives us some type of curiosity or true exploration. That's typically where we've been dismal. So I don't have an answer, but I think that is the holy grail, right? The curiosity-driven and efficient exploration. Nice. Yeah, Mario, go for it.
One, is it? Yeah.
I guess you're allowed to do this. Yeah.
So I'm allowed to do that. So what, from a bigger picture perspective, aren't all these models undergoing genetic evolution? With the fitness function, that's how much people use them, and
Yes.
they get
Yes. That's a very nice.
So there's an overarching
Yes.
fitness function that's being optimized in a sense.
I think that's really interesting way of thinking about this concern I put up top. So, so going back to what Andrea is saying, we're not very good at doing multi-step exploration where we don't have much data. It means that who designs the interfaces that people interact with the wider environment in will probably get the most data. And who uses certain models will give more data trajectories. And so that will give much more pseudo-supervised, where we tend to do better so that we can learn a reasonable pattern. But it does end up being back in the genetic algorithm, right? Like survival of the fittest almost. So it also means you should care about how you design the interface, because that will dictate a lot of how smart your algorithm will end up being. But I think it has a lot of implications for this first sentence. Yeah, nice. Okay, and I think I pass over to Ramon.
Yeah.
So nice.
Thank you.
Thank you.
Hi guys. Okay, so we're almost there. This is a tradition. It won't be very slow, hopefully. So this works as follows. I'm basically a Muppet here. I'm representing the organizers. There has been some forms that you have filled. I barely look at them. I also didn't do the slides, so I just try to power through it and see if nothing surprises me. Okay, so this year we had a bit less participants than usual, but more applications. It was a bit weird. That doesn't happen, but I think it's probably the entire world context is a bit weird right now. So we're going to just basically ignore that. But as always, people from around the world, fundamentally more Europe-centric, which is understandable. You're closer. I think that for the first time we reached 40% female, or maybe in the past we got higher than that. Like it's the percentage of female attendees. Did it ever reach 40? It's definitely better than last year's. Industry is more or less like it is. You can see here a map of where we come from. It's great that we always get people from every place. I think more people from Russia this year for some reason. I honestly, I don't know. I asked some of you, but nobody gave any convincing explanation. So, yeah, it's always great to have people from all around the world, and you always get even more than this. Okay, so in general, I think people were happy. If you were wondering what your peers were thinking, I think there was not terrible bad feedback in general. Everybody was happy. I think that probably more information would have been helpful. I think some things we did a bit late. In the labs, for example, I think some people spend too much time installing and things like this on the first day. Probably we could be more proactive. This is definitely things we can improve. I think the poster sessions look great this year, and I think people were in general very proactive and interacted a lot. And I think that maybe we can even think about expanding that. Okay, so ratings in general, great. I think some of the best rates we have gotten. The number of responses was not super big. I think maybe around 40. But in general, people were very happy. The morning lectures, they all were great. We always have this thing about, we always been like a very broad school in terms of the types of applicants, which means that you have a very diverse set of backgrounds, which means that nobody's happy because it's either too hard or too easy, or so that's very hard to equilibrate. I don't think that there's a solution for that. Again, like sometimes people want less math, sometimes people want more maths. We do what we can. We try to offer a bit to everybody, right? So on average, I think everybody was happy. I think also for the monitors, it's like probably one of the best looking scores I've seen. So that's great. Very happy about this. The scores for the labs were also very good. You probably, I don't know if you know, but this year we roll out the multimodal day for the first time. It's our first year of multimodal day. And I think from what I got, it really worked and people were happy. Also, it has photos, which I can tell you that makes it much easier. Like language is very cool, but just looking at a sentence is a bit boring. And now we can put cats and dogs and whatever. And it really makes like the guide look much better. So improvement of the labs. Recaps, I think in general we improve a lot in recaps. That was a very consistent feedback. The illustrations, you see, I was telling you, like with language, there's not much illustrations you can do. I can plot you like, I don't know, some sort of gradient thing, but now that we have image, we'll definitely probably increase the number of cats and dogs and stuff like that. Notebooks, we thought, I don't know if anybody got to the point of using a Google Colab, but it's something that we probably will grow up in the next years, depending on how easy it is to use, right? And yeah, definitely that's on us. I think that we could have been more proactive with the labs because we were preparing the new multimodal day. We basically did not notify the students a bit early on about the labs, right? Next year, for the next batch, we're going to bug you about installing and all those things. Food, again, I think that everybody's normally happy with the banquet and things like this. It's always hard to have like what everybody likes, more vegetarian options, halal, kosher, all these things. Every year we try to do it a bit better, but it's impossible also to kind of have everybody happy. I have to say, having lived in Portugal for 7 years, the situation in Portugal has gotten much better in terms of having diverse food. Like it's a bit more international. I said like before, they would look at you a bit weird, right? So yeah, fruits, bread. I love those chocolate kind of things. Like I ate like 3 before coming in. Like
It's like, come on, allow yourself. This is not your normal Monday, right? So yes, eat a bit more. It's fine. Queues very long. Yeah, cafeteria. We used to have two. Now we have one, and there's no much solution there, right? That's what we can do. So more time to eat. Yeah, sure. Yeah, but it's very hard to pack everything, right? That's the situation we have. Better level for foods. I think that the people on the cafeteria are super helpful, like so active. They want to fill your plate. I don't know if it happened to you, but they just won't take a no. You say no, yes. You're going to eat this, and no rice, and so I think in general, very happy. Banquet is great. Has always been great. We never do speeches. We never do things. I think we just roam around, and yeah, I think it's enough, right? Great food, great wine, so it always works. Yeah, this place is actually pretty good. You're not that many. Like I've seen like much more people, and it still works. Air conditioning this year, somehow it was a bit warmer. I don't know for what reason, because this is an automatic system. So it's not like we can go and then switch things off. We need to call people to just change everything. Too hot, too cold is the variance thing, right? There's no way you're going to be happy about this. Well, I can tell you one thing. Like in the first years, we didn't have air conditioning. So just think about that. So it got better, right? Too hot, too cold, but there's at least air conditioning. And sometimes too crowded. You should see other years. Like this is definitely very good. The number of monitors per student is great this year. Topics, yes, like agents, ethics. Probably nobody said reinforcement learning. Okay. Explainability. There's a very limited amount of days. Well, one, if you're astute, you can see there's one clear sign that this was done very last minute. If you see the photos here, you might realize one of the photos is actually very recent, right? So that's thanks to Fernando. Just does these things on the fly. Okay. We have the topics we have. We probably will be expanding. It's slow, but we have been consistently expanding topics, and we are always happy to cover the state of the art as it changes. Overall assessment, I think great. Yeah, like the interactivity, that we might do much better, like the more interactive lab guides, the coming late with information that we can fix. Poster sessions, that's probably doable. Consider making the school longer. It was longer. So, and then we made it shorter. I don't know why exactly, but yeah, it was longer. Like we had one day more, right? Yes. No, last year was shorter. So 2 years ago it was longer. Like we had like a 1 year more for a while, and then we made it 1 year less. Okay, anyway. So I mean, it's 15 years. We're getting old. Like I imagine, like I was there like you 15 years ago. This is a lot of time. Okay, so we're through. Time to thank our sponsors. Our main sponsors are Google and Zendesk. Then we have a lot of partners that pay for our salaries and then let us come here to do this stuff. So it's also like they're really generous. So I would. Of course, our wonderful speakers. Some of here are still around. Let's say we're always blessed with the best speakers and also people that are sociable and like to go out, and it's really fun. The monitor team, which have done a terrific job. And then finally you and all that. So thanks very much. And that's it. Time to catch a plane or maybe catch some beers. We will probably go into the park, so feel free to join and have fun. Enjoy the city.